All right, so this morning's session is an introduction to software installation. So James Gebbie-Rayet, who works on high performance computing for the Biomolecular Simulation Consortium in the UK, is going to do this.
Hello, everybody. So this talk's just going to be a sort of quick introduction to installing scientific software on your own computer. So I'm assuming that most people here are people that are either beginning out or you might have got an experimental background. So for those of you that have already played around with scientific computing already, you probably know most of this stuff already. So this talk's just going to be a short introduction. So we're just going to talk about some basic things like hardware considerations for scientific computing. We'll talk about operating systems because obviously a lot of scientific tools are pitched at more technical operating systems, the Linux-based ones. And then we'll finish on some of the software installation tools. So it's things like Docker, Conda, and that kind of stuff. And then following this session, we'll have a hands-on workshop, and this is designed to really set up your computer with some basic tools for some of the classes next week. And it's designed to be in a supported way. So, if you're on Windows, for example, and we're trying to set up some of the Linux-based tools, then we can try and deal with some of the complexities that you might encounter in doing that. It's probably best during this hands-on session that people sign off of Zoom and then come back on with support questions. But I'll give you a link to the material at the end. Okay, so for those of you that are not used to scientific computing, it's probably a bit sort of daunting as to where to start. So for those of us that are really used to working with scientific software, we kind of just brush straight through this. We don't really give much thought anymore because our computers are really well set up. We're working on things that we do all the time. But in general, what you want to do is you want to really look at what it is that you would like to do. So are you working on really little systems, or are you doing something massive, like, some of the guys that are doing the current coronavirus simulations? Some of those guys are running full S protein simulations, and these things are enormous. So there are various considerations that you might need to look at. So you always want to have your scientific problem framed. You want to know exactly what it is that you want to study, and then you can start looking at the software. So you can look into your scientific codes that are going to do the heavy, the work, the calculations, the setup tools that might accompany those, to get your simulations set up, and any analytical and visual tools that you might need to use after your simulations have run. And all of these sorts of codes will have requirements. So things like memory. Some might only work on Linux. A few might only work on Windows, and there might be some availability on Mac. So once you sort of know the sorts of things that you want to use, then you can look at if your hardware that you have access to and the operating system that is on your hardware matches what you want to do. And this talk really is just an introduction about the sorts of things that are available to you to get set up doing this. So the talk will have three major sections. We'll look at the hardware side of things. We'll look at the operating systems and what to do if you're on one and the software you want to use is available on something else. And then what we'll do is we'll look at some of the tools available for installing software. So we're not really going to go into the actual using, because that's the focus of next week's sessions. So let's take a look at the hardware. So most of you will either have access to some kind of desktop workstation or a laptop. I'm not sure if some of you have been affected by the pandemic. So I certainly have. So I'm cut off from my sort of workstation at my sort of office. So at the moment I'm using a rather underpowered laptop. But I end up sort of SSHing into my desktop and working from there. So some of you will probably have, you know, custom built desktops, and some of you will have more sort of commercially configured, you know, sort of laptop type hardware. So, and the hardware in these machines, they vary quite a lot. So, you know, you've got the sort of cheaper end processors. So I've put both the Intel and AMD ranges here because we're starting to see both processors starting to proliferate into the wider markets now. So recent years, scientific computing has been purely dominated by Intel, and you'll see a lot of the software compilation issues near enough dominated by compiling on Intel-based platforms. But we're starting to see a lot more things that surrounding the new AMD stuff. And I'll talk about some of the HPC considerations with AMD in a second. But typically what happens is the more expensive the processor you have in your machine, basically you get more processing power, so more performance, etc. So at the lower end, it might be useful for, you know, checking your email, or, you know, for say your grandma to you know, check her internet, things like that. And then at the top end, you've got your sort of power users, gamers, graphic designers, you know, your software engineers that do fairly heavy stuff. And the scientific computing area sort of starts somewhere between the two, and you know, that basically the better hardware you get, the less complications you'll have going forward, is the general rule. There are other considerations you'll need to look at as well. So if you're doing, so memory is one of them. So if you're doing some quite intensive analytical, using some quite intensive analytical codes, like some of the machine learning stuff, some of these codes can have quite a lot of quite heavy memory requirements. So if you've really only got maybe, you know, 4 gigabytes of RAM or something like that, then, you know, you might want to be looking at offloading some of this compute elsewhere. Again, running MD, if you're running sort of large systems, you know, these can require a lot of memory as well. Also, large systems probably take a lot longer to reach the point at which you're happy with how much simulation you've run. So again, you probably want to look at offloading elsewhere rather than running really large stuff on your own computer. Visualization of large systems can be quite memory hungry. So we've recently had a student that had a really underpowered laptop, and the visualization code was just crashing, you know, really a few 100,000 atoms. So if you're in the realms where you want to be looking at biological systems that are built of millions of atoms, then, you know, you probably need access to some higher powered stuff. And it's the same consideration with GPUs as well. So, you know, these are increasingly being used for compute now, and not just visualization, which we'll talk about in a second. So a lot of these Intel processors in laptops and desktops will have integrated graphics, and this can be okay for some really basic stuff. So you don't really want to be doing calculations with it, but your molecular visualizers like VMD, PyMol, you know, they'll be able to run their OpenGL sort of basic routines on really small scale stuff. If you're looking at really big systems, massive proteins, or sections of DNA or something like that, then you're probably going to need a GPU to do anything particularly useful. Again, VMD can just simply crash on it on a small integrated graphics chip. If you're doing anything like render it, so if you want to do things like ray tracing to make these nice shiny images for publication or publishing on websites or whatever, you can do it with CPU, but the rendering will take forever. Having dedicated GPU hardware can really help you to sort of produce these things in a really timely fashion. Again, as just mentioned, GPUs have been utilized in recent years for accelerating simulation codes, and actually some of the HPC facilities we have really high-end GPUs like the Tesla and Volta, and even now Ampere architecture from NVIDIA. And these, we're starting to see absolutely enormous speed-ups when running, some of them popular biomolecular simulation codes on these architectures. And a lot of the major codes, so certainly GROMACS, Amber, NAMD have just released a new GPU supported version that's it gets really good performance over previous versions. So all the major codes really have been ported to GPU architectures. So if you're lucky enough to have access to one of these rather high spec cards, or actually a cluster with them, then you'll start to produce masses of simulation quite easily. So some of the other hardware you might have access to, so depending where you are, so you might have access to national facilities, or you might have access to local high performance computing facilities. So these are basically the supercomputers. So here we've got the UK national computer, Archer. This is a Cray Intel machine. It's currently being upgraded to Archer 2, which is actually an AMD Rome architecture. So going back before to, a lot of the scientific codes have been focusing on Intel architectures. Even the HPC world is sort of, broadening out what's available. So we're starting to see lots and lots of information and lots of stuff coming from software developers that are focusing on these architectures. And then this is one example of a GPU cluster. So we've got this tier 2 machine, which is really it's a University of Oxford tier 2 machine, but it's run by STFC on their behalf. And this is an NVIDIA DGX1 cluster. So this is all GPUs, I think. So this one's Volta architecture, and Jade is going through a refresh. So it's going to be a much bigger machine. We're not quite sure on what the final architecture will be, but I think it's looking like DGX2. So we have this huge GPU compute facility available as well. And each country, and universities will probably have a similar structure that we have in the UK as well. So there'll be various HPC available for you. So what actually is HPC? So it's basically just a cluster of really high performance hardware linked by a high performance network. And that's the really important bit. So the high performance network, if you're doing calculations that are parallelized across many computers, and you want to communicate information between all these computers that are sharing the work, then the network speed is absolutely critical in achieving any form of performance in this paradigm. So these machines are quite often set up with you know, really high spec networks like InfiniBand or one of the similar products. So some of the pros of HPC, so essentially, you know, you can, if you're doing really massive simulations, you can parallelize across many, many nodes and get, so in something that might take a month on your desktop, you could probably have it done in, you know, less than a week if you parallelize across, you know, maybe a couple of hundred nodes or something like that, provided the system makes sense for the scaling level. If you have memory issues, you can offload, and these machines quite often have high memory on each node, but you can also do distributed memory where you recruit multiple nodes and share the memory across multiple nodes. So if you really have underpowered hardware for running simulations locally, you know, HPC can really help with this. A lot of the software is managed by dedicated teams. So that's people like us that go along and, you know, we do all the testing and benchmarking, and we make sure that the software is compiled properly and it really delivers a performance that it should on a given architecture. And in HPC, there's a really long tradition of you know, biomolecular simulation on HPC platforms. So there's absolutely tons of knowledge out there, you know, that you can get access to if you get stuck. Some of the cons with it, so quite often, so the refresh rate at which these machines change their hardware is quite slow. So obviously, at some point, somebody has to buy an entire machine and build it and then run it for a length of time. So obviously, this mode means that at the beginning, it's generally buying current generation hardware, and then for the next sort of 4 or 5 years, it'll always lag behind the market. But this is, you know, to be expected. You know, it's just the way things are with this game. Codes generally have to be ported by people with specialist knowledge. So, for example, if you have a code that's serial, you know, to run on something like Archer, you'd probably have to build in something like MPI. If you were going to run on something like Jade for single nodes, you'd probably have to use CUDA or OpenAC or something like that. And if you're doing multi-node, you'd also have to incorporate maybe MPI as well. And some of this, to get the real high-level performance, you know, it takes real specialist knowledge in parallel computing. But a lot of the codes used in bio, you know, this is built by people that have this knowledge or have access to it, and there's been a long tradition in this area. So a lot of the codes that you'll probably learn to use next week, they're probably already being parallelized already by people who already know how to do it. A lot of the control, so access to HPC, depending on where it is. So in universities, you might be able to quite easily get access to some HPC. Certainly the national stuff is probably controlled by some form of resource allocation panel or grant access panel or something like that. So you'd have to actually make a scientific case to get access. And in fact, in the UK, we have a sister consortium to the CCPBioSim, HEC-BioSim, which does exactly this. It basically sits alongside the CCP and runs access to, you know, specialized high performance computing for academics in the UK or academics outside that are collaborating with academics in the UK. So some of the hardware can be quite niche, so you can end up with some really strange architectures. So, you know, architectures like ARM are starting to emerge. These are becoming more sort of normal to those of us that develop high performance code, but at first it was, you know, the architecture was quite strange. And really new software can be quite tricky sometimes because so a lot of the national facilities in particular, they'll have some form of technical assessment. So they'll really want to assess whether codes are suitable for the machines that they're going on. So it ends up being quite chicken and egg sometimes, because you can't really test software on the machine that you're trying to target until you actually install it and try it. So, you know, it can be quite a strange process sometimes getting really newly developed software onto these machines, but there's usually people that can help you with this. So the other form of hardware that is starting to really become popular is the cloud. So it always ends up being a bit of a logo fest whenever we talk about cloud. So every man and his dog is pretty much trying to get into the sort of cloud game these days. Basically, the way to view it is that it's more similar to using, you know, your own hardware, but it basically belongs to somebody else. So you're basically the system administrator, and that's the only difference between cloud and your hardware. Some of the pros of it is, you know, it can be very cheap. So they quite often do per hour billing. So you simply just pay for what you use. You know, you're not actually having to buy servers and set up lots of things. You know, you don't have to install network infrastructure. So a lot of this cost is invisible to you. It's, you know, it's part of these prices you pay per hour, but, you know, you don't have that massive initial outlay. You'll quite often get the latest hardware. So I was at Scientific Computing Conference a couple of years ago when NVIDIA dropped one of their latest architectures, and pretty much when NVIDIA announced this architecture emerged in one of their sort of sessions, Google Cloud was basically then touting on their stall that they'd got this architecture available immediately. So that's how fast that sometimes you can get access to, you know, the latest stuff. You know, so there's a slight advantage there over the HPC market, that you can get, you know, access to the latest architectures really quickly. And there are tons of turnkey options. So what I mean by this is, quite often you want to just say, right, I want a web server, or, you know, I'd like a cluster where I can run various things, and there'll just be an interface with a one-click, you know, I want this, and lots of things happen in the background, and then you know, minutes later you get given, you know, access to whatever it is that you've asked for, and that can be quite, you know, useful in the regard that you don't have to actually become an expert in things like Kubernetes or various other cloud-based technologies. Some of the cons, though, is it can be quite technical. So again, you're basically a system administrator here. So, you know, if you basically install some vanilla Linux and leave it open to the internet, and, you know, bad things can happen quite easily. So you really, you know, probably need to know some things about securing things that are available on a wider internet. You'll have to set all the software up yourself. So, you know, it's all compilation, similar to what you'll be doing later today. Large data transfers can be an issue, but that's the same with HPC. It becomes more of an issue when the cloud provider doesn't have real estate in the country of where you live or close to you. You know, if you're having to send it across really long connections, it can become more of an issue, especially if you're sort of at the terabyte end of things. It's not yet fully suitable for highly parallel calculations, although this is rapidly changing, and, you know, AWS in particular actually does have its own high performance computing division now. And so the issue used to be that when you request lots of hardware, it wasn't very easy to guarantee that it was even in the same warehouse, yet alone in the same server rack. So this means you've got lots of network in between nodes, which can lead to lots of communications bottlenecks on parallel communications. But you know, they've noticed this, and and a lot of the big providers are now actually giving access to specialist HPC like architectures. So that sort of gap's closing. But you can basically make anything you want. You know, you don't have the same constraints as facilities that are run for you. So that pretty much sums up, you know, hardware considerations and what the landscape looks like. So we're just going to take a quick look at what the operating systems people might have, because I'm guessing of the 100 and can't quite see the few hundred of people that are in this session, I'm guessing we've probably got people from all backgrounds here. So typically, there are three major flavors. You know, there's the Microsoft, the Apple, and the open source community. So what we see on a sort of global level is Microsoft has the lion's share of the user base, but these are mainly sort of consumer type folks. So they'll be people that, you know, they might work in non-technical roles, or they might work in, you know, they're gamers, or they're, you know, they're just general consumers of you know, normal non-technical software. But generally, if you buy a laptop, it'll either come with one of two flavors on it. It'll either be an Apple Mac and it'll have the operating system of Apple, or you'll buy another manufacturer and it'll come with Windows. This is probably why the figures are this way. Mac has been growing for a long time. The users tend to be quite mixed. So in the old days, the users used to be very technical, a lot like the Linux people, because Mac is very similar to Linux, but very much more polished. But Apple have lately been targeting the sort of similar market to what Microsoft targets. So there's a lot of people that work now in, you know, not so technical areas that probably choose to use Mac. But the nice thing is when you look at the scientific tools, you look at the Linux and the Apple, and most of the scientific tools that we use will be available on both of these platforms. You can, as a general rule, you know, you can generally install most of the stuff that comes on Linux and Mac with Windows. It's just a lot more of a faff. You know, there's various things you'll always have to do. There are things you'll have to learn. You know, it's just easier on these platforms. And it's partly because Microsoft doesn't set its operating system up to be like a development machine by default. So if you ever install something like, you know, the code framework, the code development frameworks for Microsoft, it always feels like an optional extra rather than something that's actually integrated in, like you get with the more Linuxy based operating systems. So that's something to bear in mind. And I'm sure, you know, quite a lot of you guys will be sat on Windows machines right now. So what do you do if you are sat on a Windows machine and you find out that all the software tools you want to use are basically either, you know, they're basically available on Linux. So there's various things that you can do here. So you can either replace the operating system completely if you don't really care about, you know, which one you use. And that's what I've done on my desktop. But on this laptop here, I'm actually using virtualization. The other option is you can dual boot. So you can have Windows and Linux installed side by side. And then there's, you know, the remaining options are virtualization, and then there's a Windows subsystem for Linux. So the difficulties of using these are like this. So replacing the operating system is really easy. You basically just put the installation disk or mount image and just install it over top of the one you've got. Dual boot can be quite problematic. So I've never had problems doing this myself, but I've encountered many people that have formatted the Windows partition. They've just formatted over it by accident rather than installing Linux alongside it. So I've put this under advanced, but I'm not sure it really is fully an advanced topic. Virtualization is really easy. You basically just install a virtualization platform and then off you go. The Windows subsystem for Linux is a bit harder because there's quite a few steps to get this set up. But again, you know, there are plenty of guides, and there's one such guide linked in the workshop material later this morning. So I've put the data loss potential in here because it's quite easy to, if you're replacing the operating system or dual booting, you can either format over a one that you want to keep, or you can quite easily forget to back up things that are then subsequently replaced by a new operating system. But that doesn't happen with these two options because you're fully virtualized, you're self-contained. There can be some overheads because obviously, so when you're virtualized, you're going through a virtualization layer to the hardware. So there can be some overheads here. For example, if you've got a dedicated GPU, there might be some overheads in accessing the full sort of bandwidth of the GPU, for example, or memory. There's various overheads that you'll encounter. It's not much, but it can be noticeable when you're doing a high performance application. What's quite interesting is when you want to run both at the same time. So I'm actually on this laptop that I'm talking to you on now. I actually have Windows running with Zoom, and then I have Linux open in a virtual machine. So, you know, my desktop often looks like I've got a Windows taskbar and then a Linux taskbar up the side. So that's quite really useful if you've got lots of business processes that rely on Windows, but then your scientific stuff relies on Linux. It's a really useful way to be able to do this. So let's just take a look at what virtualization is. So there are two really big players in desktop virtualization. So there's this VirtualBox tool here that's run by Oracle, but it's an open tool. It's free to download. And then there's a VMware, which has commercial solutions, but it also has a free VMware player. I typically tend to use VirtualBox because I started on VirtualBox years and years and years ago, and I just have problems when I try to use VMware. But other people report having just as much success with VMware. So basically, how it differs is on your computer, it probably looks a lot like this. You basically got your hardware that your computer's made of. You've installed your operating system on there, and then you install your software on top, and that's pretty much standard. With virtualization, what you have is you've got your hardware, then you have the host OS, which might be Windows, then you install one of these virtualization tools, and then that allows you to then install new operating systems. So this could be Linux. If you've got a Mac license, you could probably put Mac in here, or you could even have different versions of Windows on a Windows 10 OS, main OS. And then you can install your apps inside these guest operating systems. And you can have lots of different things. So quite often, you'll see virtualized setups in, company clouds that have this sort of layout. They might not be using these tools, they'll be using the commercial variants, but, they'll be doing similar sorts of things. And this is really useful if all your software runs on Linux, but you don't want to go over the top of your Windows, keep access to your Windows. So that sort of sums up the basics of how to jump between the operating systems. So the next sort of thing we want to look at is installing some scientific software. So what's available for us? And first up, simply because it's a new technology and it's emerging, I'm just going to mention containers because you'll start to see this. It's been emerging for quite a long time as a technology, but it's becoming more and more popular in some fields as time goes on. So particularly if you're at the moment in the sort of area of machine learning and those sorts of fields, these sorts of researchers will quite often pass entire data sets and trained neural networks and various things all inside a container between, you know, research labs or scientists, and these things are designed to, you know, transplant exactly what you have on one machine onto another machine, and it just works. So there are, you know, there are two major players that you'll probably come across, but this Podman's starting to emerge as another competitor now. But the main one that you'll see is probably Docker, and if you run on HPC quite a lot, you'll probably start to see Singularity, because Singularity was developed with HPC specifically in mind. So we typically see these two technologies mostly. But what I wanted to show you is just what the difference is between, you know, virtualization, full hardware virtualization, and containers. So typically what you have with the containers is you've got your base computer, so this might be a desktop or laptop, and your main OS. Then you install one of these container engines like Docker or Singularity, and then the apps go in containers themselves. You know, you can have full microservices approach and have one container for every app, or you can have, you know, one container that's got 2 or 3 apps that work together, and this thing is fully partitioned off from apps that are installed in other containers. You can then install other architecture like networks, where you can get containers to talk to each other, and you can do file sharing and all sorts of things, but you know, organically they're separate. But the nice thing is you don't have this dual operating system overhead. So where with virtualization you'd have, you know, Linux installed inside Windows and then your app installed on Linux, you would literally just have, you know, the app running in a container with the bare bones of Linux with it, but it's running directly through this container engine on your main OS. So what you can find is, you know, you can get, you know, better performance. You can use a lot less disk and various things. So there are areas where this technology is stronger than this. You're probably unlikely to encounter it, you know, immediately in your sort of quest for scientific computing, but, you know, just be aware that this is starting to become more popular, and it's starting to emerge as a way to get things done. But I think most people that are doing scientific computing on their own laptops and desktops will probably continue to use virtualization. So probably one of the easiest ways for you guys to install a lot of the software packages is using these two tools here. So there's Conda and there's the Python package index. So these are two tools that are basically like giant repositories of software that people have compiled, you know, and got into a state where they can be delivered via these installation systems. So PyP, the package manager here, is actually the Python official index. It largely focuses on mainly Python-based stuff, and it's basically as trivial as typing pip install, and if you wanted to install the numerical Python library, it'd be NumPy. But it'd be pip install and then whatever it is that you want to install. But this, again, it only focuses on Python, really. There are some exceptions where people have pre-compiled stuff and made it available as a wheel. But generally, this tool is if something's a Python library. There's no virtual environments with this. So if you end up with like a really complex dependency web where you've got one software wants a version of, say, NumPy, and then you've got another piece of software that wants a different version of, say, NumPy, it's very difficult to install these side by side. So you'd probably use something like VirtualEnv in addition to PyPy if you install things this way, so that you can put the apps in different virtual environments. And there are plenty of walkthroughs if you encounter this particular problem. But Conda is like, so it's basically like a similar, so it's a package manager, and it's got the virtual environments, and it's got lots of other things that are part of its tool chain in addition. So you can actually install, probably most of the stuff that's on PyPy is probably on Conda, at least in the scientific and numerical sort of realms. But it actually goes to other languages, so not just Python. You've got access to many different languages in Conda. So the tool selection is probably a lot broader on Conda than on PyPy. And again, it's as simple as just typing conda install NumPy. The difference here is this PyPy often ships. So when you install Linux, you can probably install, you can probably start doing pip install basically as soon as you've installed the Linux operating system, and it all generally is there, particularly if you install Ubuntu, which is the most popular. Conda, you have to actually download and install this environment. If your tools are not available on these platforms, then basically installation remains the same. You basically either have to download a pre-built installer from somewhere, which is certainly the case for some of the stuff that you'll be installing this morning, or it then gets even worse and you basically have to download the source code and compile it yourself. So this means that you have to actually have compilers installed. You have to make sure all the dependencies to compile are there. So it's generally okay if the documentation is good. If it's a really developmental tool and they're still working on the documentation, then it can be quite fiddly and there's lots of knowledge implied. But that's basically all there is to really considering getting started in the scientific computing realms. Probably the best way to actually get going is to actually do it. So